Hi there. We just have a few more matrix related topics to get through, and one of them is special matrices. So let's add that to our new cell, to our ongoing script, and I'll say there are some special matrix commands listed in your book. Let's go ahead and do a clear CLC. Oh, mine's already clear, but maybe yours isn't. Let's say A equals 0s 5. So here's one special type of matrix. We get a 5 by 5 matrix of all zeros. One section, there you go. If you only put one number in, you get a square. But if you put two numbers in, you can get any size matrix you want. So 0s, 2, 3. Any size you like. Now I have two matrices. One is a 2, 3, and one is a 5 by 5, and they're both full of zeros. So this is a really nice way of getting a blank matrix that you can then fill in later or work with later. But this is kind of a starting place. It's nice to have it predetermined in size. Another special matrix command is ones. Maybe you want all ones instead of all zeros. This is useful when you're multiplying because multiplying by 1 doesn't change the value. So if you just put in 1, you get a square 4 by 4 of all ones. And if you put in ones with other numbers, you can probably figure out what you're going to get. Let's say 6, 2. 6 rows, 2 columns, run section. Now I have a 6 by 2 of all ones. Okay, they can get any size you like. 96. Let's do other things. So some other commands. Flip LR and oops, no 4. Flip LR and flip LUD. Flip UD. You can probably guess what these are, but we need a more interesting matrix to look at. So let's get an A equals, oh, I don't know, 1, 2, 3, 1, 2, 3, semicolon, 4, 5, 7, 10, 8, negative 1. Now I'll be able to see when I flip it around that something has actually changed. So let us make a new matrix B that is just the flip LR of A. So A is 1, 2, 3, and then 4, 5, 7, and 10, 8, negative 1. The B is the flip of that. Instead of 1, 2, 3, it's 3, 2, 1. So each row has been reversed. We can also do flip a UD of A. What do you think that does? Well, here's the 1, 2, 3. They're in the same order, but now they're on the bottom of the matrix. So it's a flip from up to down. Flip up, down. And this is flip left, right. Okay? So we can reverse matrices and turn them around and save them as new ones or rewrite on top of the matrix that we just created, for example. We may want diagonal elements of the matrix. That might be useful. So we can say D equals diag of A. So A is our 1, 2, 3, 4, 5, 7. The diagonal elements are 1, 5, and negative 1. And so we're getting that as a vector instead of but it contains elements from the diagonal. That could be really useful. We can also get the reverse diagonal, because normally a matrix diagonal is from the upper left to the bottom right, but we can reverse that by saying take the diagonal of what we get when we flip A from left to right. This gives us let's say gives other diagonal. So now we're getting from the top right to the bottom left instead. We can also do diag flip up down of A to get the other direction. Would this be the same as E? Let's check it out and see. Run section. 10, 5, 3, 3, 5, 10. Oh, I see. It's going from the lower left to the upper right. From lower left to upper right. Whew, I have to really draw a picture and think about that one. Sorry. Let's do something a little different. Let's create a matrix C that consists of matrix B, which was a 3 by 3, and the diagonal of A. So a comma here means we're getting side by side. So I'm going to have 4 columns, 3 rows. A 3 by 4. Let's comment out all those. I don't need to see them. Run section. We have a 3 by 4. 3 rows, 4 columns. Now what happens if I try to take the diagonal? If you try to take the diagonal of a matrix that isn't square, it just stops part way. So I get the 3, the 5, and the 10, and that's it. I don't get anything else. That's what diagonal means if you're talking about a non-square matrix. Let's do one kind of, it goes as far as it can. Far as it can. And let's talk about one more type of special matrix. One more special matrix. This will be a magic. So E equals magic 3. Magic matrix is quite a bit of fun. It contains all the, so there's 9 elements in a 3 by 3 matrix, and it contains all the digits from 1 to 9, all the integers from 1 to 9, arranged in such a way so that we have the same sum in every row, in every column, and in every diagonal. So a magic matrix has some special properties. There's hasn't really been a use discovered for these, but they make nice puzzles and they're interesting. It's a good way to get a matrix that has a lot of different numbers in it so that you can see when it gets flipped around. So let's do sums first. I'll sum up all the columns and see that I do get 15 for all of them. Let's add up all the rows. Remember, the rows can be added by adding the columns of the transpose. So I should get 15 for all of those as well. There they are. I do. And let's do the diagonal. Let's do sum of diagonal of E. And maybe you'll take my word for it that all the diagonals have the exact same sum. You can double check yourself. I will say that when you start nesting parentheses inside of parentheses, it gets a little hard to read, so be careful with that. Anyway, if we similarly had matrix that was magic 5, we get the same kind of thing, it's just bigger. So now we have all the numbers from 1 to 25, and so when I add up the rows, I'm sorry, this one's adding up the columns, we get a different number, but it's still the same no matter which way you slice it. Columns, rows, or diagonals. All right, those are some special commands for creating special matrices. See you next time.